Hello everyone. So in this one shot, I'm going to cover all concepts related to dual nature of radiation in matter. So first we'll go through the syllabus. So first, there is a dual nature of radiation, then photoelectric effect, Hertz and Lenard's observation, then Einstein's photoelectric equation, particle nature of light, matter wave, de Broglie's relation, and Davison-Germer experiment has been deleted this year, so you don't have to worry about this particular topic. You have to focus on these areas. So what is wave-particle duality of light? So there are some theories which believe light is a particle, and there are certain theories which believe light as a wave. So we are going to discuss some of these theories. So if you treat light as a particle, so there are two important theories. First is Newton's corpuscular theory, and second is Maxwell's Planck's quantum theory. Both these theory treat light as a particle. And there are two important theories that we have to briefly understand. First, which consider light as a wave. First is Huygens theory, Huygens wave theory, and second is the Maxwell's electromagnetic wave theory. So let us understand briefly about these theories. So Newton's corpuscular theory. So Newton proposes this theory in the year 1704. Now let us see some key points about this theory. First, the light is consists of little invisible particles known as corpuscles. And if there is a luminous source, it will constantly emit these particles. And when these corpuscles strike the retina of our eye, we have the sensation of the vision, and they travel with the speed of light, which is 3 into 10 raised to power 8 meters per second in vacuum. And the velocity changes as these particles move from one medium to the another medium, and different colors of the light are because of the different sizes of the corpuscles. So these are the key points about this particular theory. And there is one more important point, that is the rest mass of these particles is 0. So you have to keep these points in your mind. Now let us see what is Max Planck's quantum theory. So according to this theory, all matters, they absorb and emit energy in discrete quantities. And the smallest packet of energy is called quantum, and in case of light, it is known as photon. And the energy of quantum is proportional to the frequency. So Max Planck has given this relation that the energy of one quantum is equals to h times nu, where h is the Planck's constant. So h is equals to 6.626 into 10 raised to power minus 34 joules second. So this relation you have to remember. Okay, so we can say this is nothing but the energy of the photon. The another important theory is Huygens wave theory. So you must have studied this theory in wave optics. So according to this theory, if there is a point source, and if we take the locus of points which are equidistant from this point source, now the locus of these point is known as a wavefront, and the different points on this wavefront will act as the secondary sources. So these are secondary sources. Now these secondary sources will generate secondary wavelets, and these secondary wavelets will travel with the speed of the wave, which is nothing but 3 into 10 raised to power 8 meters per second in vacuum. Now let us understand the propagation of energy in the form of wavefronts with an animation. So let us see. So we have a wavefront. Now these are the secondary wavelets which are being generated, and the common tangent to these secondary wavelet give us the new position of the wavefront. So this is all about Huygens wave theory. Now let us see the key points. Whatever I have mentioned here, let us see that in writing. So first, the locus of all points, locus of all the particles vibrating in the same phase is known as a wavefront. Second point, the light travels in the medium in the form of wavefront. Third, every point on the wavefront becomes the source of secondary wavelets, and it emits secondary wavelets in all directions which travel with the speed of light. And the tangent plane to these secondary wavelets represents the new position of the wavefront. So these are the key points about Huygens wave theory, and you have to remember this. The fourth theory is Maxwell's electromagnetic wave theory. Now, according to this theory, the source is emitted, the energy is emitted from any source continuously in the form of radiation, which is also known as a radiant energy. And we have an oscillating perpendicular electric and magnetic field, and both perpendicular to the direction of propagation of the radiation. So let us understand this. So this is the example of a plane polarized electromagnetic radiation. So can you see x-axis is the direction of propagation of electromagnetic wave, and electric field and magnetic field, they are oscillating in perpendicular planes, and they are always in phase, right? So you have to remember this. And the radiation possesses wave characteristic and travel with the speed of light. And radiations are known as electromagnetic radiation or electromagnetic waves. You must have studied this in EM waves, right? Okay, so and the last point about this theory is these waves do not require any material medium for their propagation. They can travel through vacuum. Okay, now let us come to a very important part, that is photons, right? Properties of photon, and we can expect a question from this particular section. So first of all, the photons, basically they travel with the speed of light, which is 3 into 10 raised per 8 meters per second in vacuum, and their rest mass is 0. So do remember this. And the energy of photon will be given by E equals to h nu, where nu is the frequency, h is the Planck's constant. We have already studied this in Max Planck's quantum theory. And if we want to increase the intensity, it means if I want to increase the intensity of radiation, it can be done with the increase in number of photon incident per unit area per unit time. Suppose if there is an area, and let us say 3 photons strike this area normally in 1 second. Now, if I want to double the intensity, what I can do, I can double the number of photons. Suppose if we have 6 photons, now the intensity has doubled. So do remember this, by increasing the number of photons, we can increase the intensity. Now, the fourth point, suppose, is the Einstein's relativistic energy and momentum relation. Since the rest mass is 0, if I want to find the energy of photon, we cannot use half mv square, right, that we use for particles. So here we have to use this relation, E equals to root mc square whole square plus cp square, where m is the rest mass, p is the momentum, c is the speed of light in vacuum. So if we apply this equation for photons, we know that m is 0. So E comes out to be root 0 plus cp square. So this gives us as cp. So the energy of photon is equals to c times p. So the momentum of photon will be given by E by c. Or energy can be written as h nu. And we can also write this as hc by lambda. So it is nothing but h by lambda, right? So do remember this relation. It is very important relation. So these two formulas you have to remember. Momentum will be given by E by c, and the energy will be given by h nu. Okay. Now so in this particular chapter, or in modern physics, usually the energy is measured in electron volt. Now let us see how we can convert joules into electron volt, or we can say, suppose if we have given a photon whose wavelength is given in angstrom, how we can convert that into electron volt. So if we have given wavelength in angstrom, we can find the energy in electron volt by using this relation. So let us understand. Suppose if the wavelength is given as 1000 angstrom, so the energy will be 12400 divided by 1000. So this will be 12.4 electron volt. Okay, so like this we can find the energy of a photon. Okay, right. So now next concept is the rate of photon emission from the source, right? So then how many photons are being generated per second? So it will be given by this formula, P by h nu, where P is the power. So P is power and nu is the frequency, right? And lambda is the wavelength, right? And h is the Planck's constant. So do remember this formula because I have seen the direct question from this formula in exam. Next is the intensity of a point source. If there is a point source and we want to find the intensity at a distance r from the point source, let us say the power of the point source is P, then intensity will be defined as power per unit area of the wavefront. Now the wavefront which is at a distance r will be 4 pi r square. So the intensity will be given by P upon 4 pi r square. Again, very important formula. Okay, next is the force and the radiation pressure exerted by the light beam on the surface. So now let us see the first case, perfectly reflecting surface and for normal incidence. So if there is a surface, it's a perfectly reflecting surface. Now we have a photons which are incident normally. And let us say the area is A and I is the intensity. I is the intensity of the radiation and C is the speed of light in vacuum. Then the force exerted by these photons on this area will be given by 2IA by C. Do remember this formula. And if you want to find the radiation pressure, or the radiation pressure will be given by normal force per unit area, right? So here normal force is nothing but 2IA by C. And if we divide this with the area, we will get the radiation pressure, that is 2I by C. Okay. Now let us see the case of perfectly absorbing surface. Now let us say this surface is perfectly absorbing, and again photons are being incident normally. So we are considering normal incidence, and the area is A, intensity is I, and C is the speed of light in vacuum. So the force exerted by these photon on this area, so that force will be in the downward direction. Similarly, in this case, again, in the perfectly reflecting surface, the force is again in the downward direction. So in this case, the force will be given by IA by C. And if you want to find the radiation pressure, it will be I by C by dividing force with the area. Right. So now let us see the next concept. So we are done with the photons. So you have to remember the formulas that we have studied. Now let us see this concept. So de Broglie hypothesis. So according to de Broglie, if a wave or light has a particle nature, so we can assign wave nature to a particle. So according to him, that the particle property, which is momentum, can be related to the wave property, that is wavelength. So he has given a formula with which we can find the wavelength associated with a particle. So the de Broglie wavelength will be given by h by p, where p is the linear momentum. So p is linear momentum, and we know that p square by 2m is nothing but the kinetic energy. So we can write p in terms of kinetic energy as root of 2mk. Okay, so we can write p as root of 2mk. Now suppose if we have a charged particle. So in case of a charged particle, say we have a positively charged particle, and if we accelerate this positive charged particle through a potential difference of say v, then the kinetic energy acquired by this positive charged particle will be the charge of this particle times the potential difference qv. So this is nothing but the kinetic energy acquired. So we can write kinetic energy in terms of potential. So it will be k will be qv. So we can also write linear momentum as root of 2m qv. Right? So do remember this formula. And suppose if we want to find the wavelength of some of the important charged particles, say electron, proton, deuterium, alpha particle. So what we can do, if you see this H, M, and Q, these are constant for that particular particle. So if we simplify that, the de Broglie wavelength for electron will be 12.27 upon root V, where V is the accelerating potential. And so with this formula, we can find the wavelength in angstrom. For example, if in case of an electron, if V is 100, in that case, the lambda will be 12.27 divided by 10 angstrom. So it is 1.227 angstrom. So I would recommend to remember these formulas, because otherwise, if you convert these known factors in exam, it will take a lots amount of time. So I would recommend do remember these formulas. So in case of proton, the factor will become 0.286. In case of deuterium, it becomes 0.0202. In case of alpha particle, it becomes 0.101. Right? So do remember these formulas. Now, sometimes they in exam they will ask you the de Broglie wavelength of an uncharged particle or a gas molecule. Now let us see what we can do in that case. So in case of a gas molecule, we know that in kinetic theory of gases, we have seen the average kinetic energy is given as 3 by 2 kBT, right? So we can replace kinetic energy with 3 by 2 kBT. So we can write root of 2mk with root of 2m 3 by 2 kBT. So this 2 will get eliminated. So we'll get root 3m kBT. So do remember this formula. So in photoelectric effect, let us see what we're going to study. So first we'll see the observation of Hertz and Leonard and Holbeck. Then we'll see the important terms related to this effect, that is the work function, threshold frequency, and threshold wavelength. Then we'll see the experimental setup. Suppose if I want to observe this effect in a lab, so what should be the experimental setup for that? Then the Einstein's photoelectric effect equation. And then we'll see how the current or the photocurrent varies with the potential difference, and what is the concept of saturation current and stopping potential. Then we'll see the graph of saturation current with the intensity, and then the graph of stopping potential with the frequency. So let us see what is a photoelectric effect. Suppose we have a metal surface, and we know that in metals we have free charge carriers, which are roaming freely inside the lattice. So suppose if we incident photons of sufficient minimum frequency, so if that photon is being absorbed by those freely moving electron, loosely bound electrons, so there is a possibility that that electron will come out of the metal surface. And this phenomena of ejection of electron from the metal surface is known as photoelectric emission. And the electrons which are coming out are known as photoelectrons. Now let us see how this effect was discovered in past. So first let us see what is the Hertz observation. So Hertz, like we all know Hertz, he was responsible for generation of electromagnetic radiation in lab and also receiving those electromagnetic radiation wirelessly. So Hertz was doing his experiment. So he was generating electromagnetic wave and receiving electromagnetic waves at the receiver end. So at the receiver, how do we know that we have received some signal? So there is a spark between these two electrodes because there will be some EMF induced in this receiver. If there is an EMF induced, there will be a strong electric field in this region, right? There is a strong electric field. And due to that strong electric field, there will be some, you can say, dielectric breakdown of the medium. So there will be charge carriers created in this region. And due to that, there will be a spark. So by accident, Hertz observed that if we incident ultraviolet light on the receiver, the spark has enhanced. So basically it becomes bigger, right? So that was the first observation of Hertz. So Hertz published about this observation in a research paper, and then based on this observation, Lenard and Helmholtz carried out some experiments. So now let us see what Lenard has done. So Lenard has taken a metallic plate, which is known as an emitter plate. This is a emitter plate, and this is the collector plate. And he has placed these two plates in an evacuated glass tube, right? Evacuated glass tube. And then he incident UV rays on this emitter plate. And he observed that there is some current in the circuit, right? It means some charged particle has come out of the emitter surface and they move from the emitter to the collector plate and constitute the current. So that is the observation of Lenard. And then Helmholtz further do more experimentation, and Helmholtz used a negatively charged zinc material. So if we incident say UV rays, so he incident UV rays on this negatively charged zinc plate, and he found that this negatively charged zinc plate after some time becomes neutral, right? And if it keeps on adding photons, or if it keeps on bombarding this with photons, eventually it becomes positively charged, right? So from these observations, we come across this phenomena. And at that point of time, they were not aware what type of particles are coming out. So later, J.J. Thomson discovered electrons, and then it was like they came to know like these particles are electrons which are coming out. So as electrons are coming out, the material will become more positive, right? It becomes more positively charged. So I hope these observations are clear to you. You have to just have some brief idea about these observations, because there can be some theoretical question on Lenard and Helmholtz observation. Right, so now let us see the terms related to photoelectric effect. So first we'll see the work function, then we'll see the threshold frequency, and then threshold wavelength. Now let us study these terms one by one. Now work function. So work function basically is the minimum energy required to remove the most loosely bound electron from the metal surface. So it is denoted with phi, right? And we should also remember that if we want to eject more electrons, we have to incident more photons. So if we talk about increasing number of photons, it means we have to increase the intensity. So do remember this. So the energy of photon incident on metal will not necessarily cause emission of the electron, even if its energy is more than work function. So what does it mean? Suppose we have sufficient energy, photon has sufficient energy, but suppose if that photon is being absorbed by an electron which is not loosely bonded, in that case, we'll not able to remove that particular electron. Okay, so do remember this. So that's why the number of ejected photoelectrons is always less than the number of incident photons of sufficient energy. But if nothing is given in the question, you can assume that the number of photons incident is same as the number of photoelectrons ejected. Okay, right. So threshold frequency is the minimum frequency required to carry out the photoelectric emission. And we can find the threshold frequency if work function is given to us. So it is phi upon h. So we have to remember this formula. Now the threshold wavelength, you can say it is the maximum wavelength that is required to carry out the photoelectric emission. So it is the, you can say the wavelength corresponds to the threshold frequency is nothing but the threshold wavelength. So we can also call it a cutoff wavelength. So cutoff wavelength, and for a given metal surface, threshold wavelength is the longest wavelength at which the photoelectric emission is possible. Right. So if we decrease the wavelength, then the frequency will increase. So we can say if we have a wavelength which is less than threshold wavelength, in that case the photoelectric emission will happen, right? Okay, so we can find threshold wavelength by this formula, where Hc is, or you can say the threshold wavelength is equals to Hc upon phi. Okay. Now let us understand the experimental setup that is used to study photoelectric effect. So let us go through this animation. So this is the setup for photoelectric effect. So we have a emitter plate, this is the collector plate, and these two plates are kept in a evacuated glass tube. What is a evacuated glass tube? Which does not have any pressure. So it is nearly vacuum. Now we have a source and we can alter the intensity. So how we can alter the intensity? By changing the number, or by increasing, if we increase the intensity means we can increase the number of photons which are being incident on the emitter plate. So let us have some intensity, right? So I am keeping intensity as 50%. Now this is the intensity. So can you see, but there are no photoelectrons which are coming out. Why they are not coming out? Because the frequency is not sufficient enough. So at present we have 612 nanometer of wavelength. So if we decrease wavelength and increase intensity, electron can come out, right? So let us see. So if we decrease wavelength and increase frequency, there will be a particular wavelength at which the electrons are coming out. Can you see? And when these electrons reaches the collector plate, they constitute a current, and this current is shown here as 0.019. Okay, right. Now what would happen if I double the intensity? If I make the intensity 100, at present it is 50% and the current is 0.019. So if I double the intensity by making it at 100, so can you see the current has also become double. So it becomes 0.039. Earlier it was 0.019. So it is all, the current will almost get doubled, right? So now look at the speed of the fastest electron. So just observe the speed of the fastest electron which is coming out. So if I increase the wavelength, increase the frequency of the radiation for the same intensity, let us say we have increased. Now can you see the speed of the fastest electron has also increased? So we can say the most loosely bound electron, its kinetic energy will increase as we increase the energy of incident photon. So these concepts you have to remember. I think now we have enough knowledge, and now we can discuss the important graphs for photoelectric emission. So if you are clear about the working of photoelectric effect, now let us see a very important equation, which is Einstein's photoelectric equation. So according to this equation, and this equation is valid for most loosely bound electron. Suppose if we have a metal surface, and let us say this is the most loosely bound electron, and if we incident photon of energy, say h nu, a part of the energy of this photoelectron will overcome the work function, and the remaining energy will increase the kinetic energy of the loosely bound electron. So it will come out. So this electron will come out with certain, let's say the energy is kmax, right? And the work function of this metal is phi. So we can say h nu is sum of the work function and the maximum kinetic energy. So the maximum speed of the photoelectron will be V max. So from this equation, we can find the desired physical quantity. Okay, right. So as we have seen that Kmax is nothing but h nu minus phi, where h nu is the energy of the incident photon, phi is the work function, Kmax is the maximum kinetic energy. So if I plot the graph of Kmax and the frequency, so in this equation, phi is constant, h is constant. So we can say it is of the form of y is equals to mx minus c. where the y-intercept is negative and the slope is nothing but h. So if we plot this, let us say we have two metals, so metal 1 and metal 2. So if this angle is theta and this angle is theta, so we can say tan theta is nothing but h, and the y-intercept is nothing but the work function for that particular metal. So this will be 0 comma minus phi 1 and this will be 0 comma minus phi 2. So if you plot kinetic energy versus frequency graph for any metal, all graphs will come out to be parallel to each other because they will be having same slope. So do remember this graph. Now let us see a very important term, the saturation current and the stopping potential. So let us understand that. So suppose we are plotting a graph of the photocurrent. On the y-axis we have photocurrent. This I is photocurrent, and on the x-axis we have the potential. Now what is the potential? For example, this is our emitter plate and this is the collector plate. Let me call it C and this as E, right? And we incident photons on this emitter plate. Now what would happen? The electron will come out. And let us say we have a battery whose polarity is like this, and the collector plate is positively charged. You can say collector plate is at high potential and the emitter plate is at low potential. Now due to this potential difference between the emitter plate and the collector plate, there will be an electric field. The electric field is in the left direction. Now this electric field will exert force on the photoelectrons in the opposite direction. So as the photoelectrons come out of the emitter plate, there will be a force in the right direction, and these photoelectrons will accelerate in the right direction, and then they will get collected by the collector plate. Suppose let us increase the value of this V. So if we increase the value of V, what would happen? Suppose if there were 100 photons initially which were ejected, and out of these 100 photons, let us say 50 photons are able to reach the collector plate. Okay, but if we increase V, the field will increase. So as we increase the field, more photoelectrons will be able to reach the collector plate. So as more electron reaches the collector plate, the current or photocurrent will be more. So can you see, for a given intensity, as for zero potential, if there is no potential, still there will be some electrons which are reaching the collector plate and constitute the current. But as we increase the potential, the number of photoelectrons which are reaching collector plate will increase, and there will be you can say there will be a potential difference at which whatever electrons which are being ejected are reaching the collector plate. Now this current is known as, so this value, right? This current is known as the saturation current. So we can say saturation current is a current when all ejected photoelectrons are reaching the collector plate and constitute the current. Similarly, if we increase the intensity, then the number of photoelectrons which are being ejected will increase. So can you see the graph for I2, where I2 is the intensity, I2 is greater than I1. So in this case, the graph, you can say the value of the current is more. And it is quite obvious because more photoelectrons are reaching the collector plate. And in this case, the saturation current will also increase. So we can see the saturation current depends upon the intensity. So do remember this graph. Now let us see what happens if we increase the intensity and what happens to the photocurrent. As we have seen in this graph, as we increase the intensity, the photocurrent, the saturation current has increased. So we can say, as we increase the intensity, the photocurrent will increase, right? So do remember this, it's a straight line. Now what is the stopping potential? So we can say it is the minimum retarding potential required to make sure even the most energetic photoelectron is not able to reach the collector plate. So let us see. Suppose if we make the emitter plate at at high potential, right? Make it as positive, and the collector plate as negative. Something like this. Now what would happen? So there will be a field in the right direction. Now this electric field will exert force on these photoelectrons in the opposite direction. So this is the direction of force. Now suppose we have the most energetic electron. So this is at high potential and this plate is at low potential. And we have a photoelectron and let us say its speed is maximum, right? And its kinetic energy is Kmax. Now this electron will experience a force in the opposite direction. It is going in the right direction, but it will experience a force in the left direction. And suppose before reaching the collector plate, its velocity becomes 0. So can you see there is a decrease in potential, there is a decrease in kinetic energy. And that kinetic energy has gone in increasing the electrostatic potential energy. So we can say this K max is nothing but E times the potential difference. So let us say the potential difference is V naught. So the maximum kinetic energy of the most loosely bound electron will be E times V naught. So we can write it like this. So if I show this in the graph, let us consider for I1, right? I2 is greater than I1. These are the intensities. So we have seen up to this particular mark when the potential is 0. Suppose now we have a reverse voltage, right? So as we have more reverse voltage, the field will become more in the reverse direction and it will decelerate electron even more. And there will be a potential at which the photocurrent becomes 0 because even the most energetic electron is not able to reach the collector plate. So here the you can say the current will become 0. And can you see one more thing? For a given metal and for the same frequency, right? For the same incident frequency, the stopping potential is same. So let me show you. So we have H nu is equals to phi plus K max, and this K max can be written as E times V naught. So can you see if the frequency is same, work function is same for a given metal, H is also constant, E is also constant, the stopping potential will not change. So we can say stopping potential does not depend, stopping potential does not depend upon intensity. It will remain same for the same frequency. But as we change the frequency, the stopping potential will change. So this is for same. So it is clearly mentioned here for same frequency. So do remember this graph, right? How to compare if we have different intensities. Okay, right. So now let us see the graph of stopping potential with the frequency. And we have just seen this formula, right? So V naught is equals to H by E nu minus phi by E. So if I take this angle as theta and this angle is again theta. So this is metal B and this is metal A. And this is nothing but the slope, right? So this is slope and this is nothing but the y-intercept. So these are the values, right? So it's a linear graph because it is of the form of y is equals to mx minus c, where m is the slopes and c is the y-intercept. So I hope this graph is also clear to you. And suppose if I want to find the threshold, if this graph is given to us and we want to find the threshold frequency, it will be given by the x-intercept of this graph. So these are the threshold frequencies. So for metal, for different metals, the threshold frequency will be different, right? Because the work function is different for different metals. I hope the concept that we discussed in this video are clear to you. See you in the next video where I'll cover atoms. Thank you.